All right, next in the unit we're going to look at the fundamental theorem of algebra. And we kind of looked at this before just in sketching the graphs. All the fundamental theorem of algebra says is that the degree of your equation is the same as the number of roots that you have. And today we're going to look at what happens if the picture seems like it doesn't have that many roots. So if you look at this first equation, what's the degree of the polynomial? Well, you look at the highest exponent, it's a 4, and so that's the degree of the polynomial, 4. How many roots should, that's a typo, should it have? It should have 4 roots. So next we're going to go ahead and draw a sketch of the graph. So here's what the graph looks like on the calculator, and you can go ahead and draw a little sketch of it on your paper. So it looks something like that. And if you look at the picture, it appears to only have 2 roots. It's got a root right here and a root right there. And if you look at those 2 roots that it has, each of them has a multiplicity of 1. Each root has a multiplicity of 1. So just looking at the picture, it looks like this really should have a degree of 2, but it has a degree of 4. So, So where are the rest of the roots? It means the other roots are imaginary or complex. So 2 of the roots are real and 2 of them are fake, basically, and that's why they don't show up on the graph. So there are 2 more answers for x. We just have to kind of solve for it by hand. So next it says, how do I find the complex roots? Well, here's what we do is we're going to go ahead and graph it like we just did. So we would look at this graph right here, because the first example is that problem. And then we would look at the answers, the roots that we do have. And if you count over here and count right there, one of the roots is -5, the other root is +3. All right, so that's the equation that we're looking at. So if you guys remember how roots work, they're basically, another way we could talk about them is we could say they're factors of the parabola. So one factor would be like x plus 5 in parentheses, another factor would be x minus 3 in parentheses. That's how you would have actually found these roots. And so what we want to do is we want to divide by the factor that we already have, and we want to see what factors are left over. Like if you wanted to know, you could say like 20 is divided by 2, which leaves you 10, so one of the factors of 20 would be 2. 10 is divisible by 5, so 5 would be another factor, and then when you finish dividing that, then you'd have 2 left over, so the factors of 20 could be 2 and 5. And we're going to do that same sort of thing here, where we're going to divide by the roots we have and break it down until we get to the imaginary part that's left over. So go ahead and put -5 in the little box. And the way that we have divided these in the past is using synthetic division. So I'm going to go ahead and set that up. So when I do synthetic division with this, I'm going to go ahead and drop down my number first. My remainder over here is going to be on the end. Okay, so 1 times -5 is -5. When I add those, I get -3. -3 times -5 is +15. When I add those, I get 4. 4 times -5 is -20. When I add those, I get -12. -12 times -5 is +60. When I add those, I get 0. Anytime you are plugging in something that is an actual root, you will not have a leftover. So if you get anything other than 0, it means you did the problem wrong. If you get 0, it means that you're on the right track. So anytime we divide by an actual factor of something, it goes in evenly. For instance, the example 2 is a factor of 20 because 2 divides into 20 evenly. 3 is not a factor of 20 because 3 does not divide into 20 evenly. So as long as we don't have any leftovers, we're good. So I went ahead and I did the root of 5. Now I'm going to divide again, but I'm going to use 3 this time. So I'll put 3 in the little box, and I'm just going to use these numbers here. So as I continue to divide, what I'm dividing by gets smaller and smaller and smaller. And if we were, I'll go ahead and put the x's in there just so you can see them. This would have been, since the original was x to the 4th, this would have been x to the 3rd, x squared, x, just the number, and then no fraction on the end because no leftovers. So now we're doing the next problem. So I'll go ahead and drop down the 1. That's 1. 1 times 3 is 3. those add up to 0. 0 times 3 is 0. 4 plus 0 is 4. 4 times 3 is 12. Those add up to 0. That's exactly what I wanted. So now if I compare the red part with the blue part, I want to drop my exponent by 1. So x squared, 0x, and 4. So I'm going to say this is x squared plus 4. So if I was to write this problem out with all of the factors, the first two roots would have been from x plus 5 and x minus 3. And then this last part here is x squared plus 4. And the way, if you guys remember, that we find roots when it's written in factored form like that is we just take each set of parentheses and we make them equal 0. Well, I don't need to do the first two. I already did those. So I'm just going to say x squared plus 4 equals 0. And now I'll go ahead and solve for x. So I'm going to minus 4 on each side. I guess I can show my work there. So x squared equals negative 4. And then I'm going to take the square root of x squared to get rid of the little squared there. And I'll take the square root of negative 4. And remember, anytime you have a square root, you should have a plus minus in front of it. So I have x equals plus minus the square root of negative 4. Hopefully you should recognize that negative should be a positive and put an I in the front. And then the square root of 4 is just 2. So that means that x is going to equal positive 2i and negative 2i. And so those are our other two answers. Now we can go back to the top and write the other two roots that we have. So positive 2i and negative 2i. And now if we look at the real roots, negative 5 and 3, and the imaginary or complex roots, 2i and negative 2i, now that completely adds up to the degree, which was 4. So that means we have found all of the roots now, the ones that show up on the graph and the ones that don't. All right, here is the next example. So if I can see from the equation that I have a degree of 3, that means that I should have 3 roots or 3 x-intercepts. And if I don't have 3 of them, then that means that I definitely have a complex root in there somewhere. And if you look at the picture of the graph, I went ahead and put it up. With the way my window is, I can't see all of the picture. It doesn't matter because all I care about is the x-intercept. And that x-intercept right there looks like it's at positive 3. And if you can tell, that's a multiplicity of 1. That is definitely a straight line going through that point. And so that means we do need to use synthetic division to try to find the other two roots that did not show up, meaning that there's 2 complex roots in this problem. So 3 goes in the box, and then I have 5, negative 17, 9, and negative 9. All right, so I dropped down the 5. 5 times 3 is 15. When I add those together, I get negative 2. Negative 2 times 3 is negative 6. When I add those together, I get 3. 3 times 3 is 9. When I add those together, I get 0, which is what I expected. Now, since I only had one real root, I don't need to go ahead and divide these again. I'm done. So now I can just add my x's back in there. I have x squared is going to be the first one, since it originally was x to the third. So x squared, plain old x, and then plus 3. So that would be like one factor in parentheses. The other one was x minus 3. That's how you get the positive 3 that was written right here. So remember, the way that we would solve these is we would take each set of parentheses and make them equal 0. I don't have to do that one because it's already been done. This other one, 5x squared minus 2x plus 3. These answers are going to have to be complex. They have to be imaginary, which means I'm not going to be able to factor that to solve. If I was able to factor it to solve, then it would have been a real answer. So the only way to solve this, the way it's a trinomial, has 3 pieces, is we're going to have to do the quadratic formula on this one, and it's guaranteed going to be an imaginary answer. So first I'm going to go ahead and find my discriminant. So there's my b squared minus 4 times a times c, and I see that my discriminant is negative 56 when I multiply all of that out. And so when I plug it into the quadratic formula, I get positive 2 plus or minus square root of negative 56. I'll go ahead and make that a positive and put an I in the front. And that's divided by 2 times a, so that's divided by 10. And so those are my other 2 answers to make up for the 3 answers total. So up here, x equals 3. It also equals 2 plus I square root 56 over 10. and 2 minus I square root 56 over 10. And so there's all three roots adding up to that degree of 3.